So for this video, we will be talking about integration for inverse function. So for the past weeks, I already been giving you the formulas or a formula sheet for integration, and we have been taught, or we have not executing uh, integration for inverse functions such as logarithmic function, exponential function, hyperbolic functions, etc., and others. No? Um, it is also been good that we also have been tackled substitution rule before we proceed with inverse function, because yeah, we do need that method to execute inverse functions. Well, some of the integration formulas may not been exposed in, or may not been tackled in this video. However, at least here in this video, you might be aware, or you have you might have you may have a knowledge to how to execute uh, integration for inverse functions. So yeah, you have to still also scan your integration formulas for you to execute all of the situation for inverse functions. Okay, so let's proceed. So let's go ahead with this integration formula for exponential function. While for the general rule for exponential, we have the integration of uh, exponential of x dx, which is a conversion of, which is equals to exponential of x plus c. Okay, yeah, right here. Or if your x here has a corresponding value, or you have a composite function here, you may say that it can be as integral of exponential of u du is equals to exponential of u plus c. Right? So that is the equivalent integration formula. So this is familiar to you in differential calculus. So if you integrate this, it will, yeah, equivalent to just the EU. So let's go ahead for an example. So we need to evaluate the integration of x squared multiplied by the exponential of x cubed dx. And while we have this value also, and this value also, you notice that the value of the exponent of the Euler number, or the exponential function, is an x cube, which is a function of. So yeah, to execute this, we need to do a substitution rule. We need to choose, we need to use another variable so that we can simplify the equation. So here, let's just say that your u here is x cubed, and your du here is 3x squared dx. Yeah. So yeah, from the equation of x squared ex cubed dx, so we have a conversion of u here, and we need to replace all the variable x with u, and we have a conversion here with this two yeah, terms, and there is a numerical coefficient here. So what happens is, if we separate the two terms that we created with equation 1 and equation 2, we have here ex cubed, then we need to add 3, no? 3x squared dx. Since we are multiplying here with 3, then we add a reciprocal of it to make it equal or balance. So yeah, so now we now substitute the value of the u. So we have here a translation of u here, which is equals to the integral of u then du. And yeah, from the integration formula, we know that it is equal to eu plus c. So that is our answer. Or if you are hesitant with the value of your constant, it is just 1/3 of eu plus c. It is just equal. Okay. Let's proceed. Okay, so find the area of the curve y is equals to e exponential of negative 3x from 0 to 1. So since we already know that application of integration is finding the area of the curve in a Cartesian plane, so we are just trying to integrate this with a given of an upper and a lower limit, right? So, but before we translate it to the integral equation, let's just have conversion of the graph of the y is equals to e raised to the power of 3x or exponential of 3x. Yeah. Well, I am using here an Microsoft Math so that we can graph here. So let me just uh, show you the graph. So the graph of y is equals to negative exponential 3x is from 0 to 1. We have here the value of 1. I think the um, the root here is 1.5, and we have here uh, a curve around here. So yeah, taking the area from the limits of 0 to 1 is just taking the area from here, which is 0, to here, right? So yeah, we are solving the area of this curve around this limit. And so the translation of that in integration is just the integration of exponential of 3x dx from 0 to 1. And so our value here is negative 3x for exponential. We need to also apply the substitution rule here. So by substitution rule, which is u is equals to negative 3x, our du is equals to negative 3 dx, right? So separating this, no, I will just go directly with the substitution rule. So since we are adding a multiply negative 3 here, we need to also multiply negative 1/3 outside. So negative 1/3 integral of e u du from limits to 0 to 1. Alright. So we also need the I. I'm sorry. So we need to also replace our limits in terms of our u here. So when x is equals to 0, our u here is equals to 0. So when x is equals to 1, so our u here is equals to negative 3. So when sorry, negative 3 times 1, which is equals to negative 3. So that is equivalent to 0 here. This is 0 and this is 3. And since by writing correctly the integration, so we need to take the reverse of it, no? upper limit should be a higher value than the lower limit. So when we reverse this by integration property, it becomes a negative integral. So what happens here? It becomes positive. So that is 1/3 of integral of EU, ano, um, exponential of u. Just erase here that one. Okay. So integral of exponential of u du from -3 to 0. Okay, so we can now integrate this. So that is equivalent to EU limits from -3 to 0, and that is equivalent to 1/3 times E0 minus e raised to the power of -3, which is equivalent to 1/3 of this. Okay, so that is exponential of 0 minus exponential of 3. So that is around negative 19.086, right? Times 1/3. 19.086 times 1/3, which is equals to negative 6.36, and that is our value. Okay. 0 to 5. Oh no, yeah, this is, I'm sorry, so this should be equal to, let's just erase this one. This should be equals to 0.95021, which is equals to, if we divide it by 3, that is around 0.3167. So that is our final answer. I have mistakenly input in the calculator, so that's one thing to consider. So yeah, that is our answer for this problem. So, and that is the equivalent area for this one. So let's proceed. So here we have also integration formula for the logarithmic function. And while we are considering for the integration of reciprocal value, so integral of 1 over x dx is equals to the natural logarithm of x plus c. And also we can write here if our value for your x has a equivalent composite function. So that is 1 over u du, which is also equals to ln absolute value of u plus c. Right. If you're familiar also in differential calculus, that is just taking the differential of ln u, which is equals to 1 over u plus c. Ano, no plus c. Naanad naman lang po sa just 1 over u. Okay. Okay, so let's have a example here. So how about this? So we have to evaluate the integral of the x all over x squared plus 1 dx. And yeah, since we need to aim for the 1 over x times dx, or uh, 1 over u du, so that we can have a value for we can integrate this easily, which is equivalent to ln u plus c, diba? So yeah, by substitution rule, this should be your u here should be x squared plus 1. So just a quick tip, no, here your value here is we need to cover all the denominators so that what's left is the uu. So while your du here should be equal to 2x dx. So we have x dx on the upper part of the integral, so, or the numerator, which is the x dx, and we need to multiply it by 2 so that we can replace it by du. So yeah, so equivalent for this expression is equals to, since we have to multiply inside by 2x, I know 2, so we need to multiply it with 1/2 to make it equal. So we have here x dx all over x squared plus 1, then sa 2, then that is equivalent to du over u, which is equals to 1/2 of ln absolute value of u plus c, or 1/2 ln absolute value of u plus c. Okay, so that is our answer. So next example would be calculating the integral of ln x over x dx, limits from 1 to the e, or the Euler number. So how can we integrate this? Okay. Okay. So again, we need to use a substitution rule. Okay. So what could be the possible u here? So the possible u here would be ln x, and so differentiating the u, the ln x, would be equal to 1 over x dx. So replacing the ln x here would be this one, and while for our du, this one. Okay, so also since this is a definite integral, you need to also change the value of your upper and lower limit. So at 1, that will be ln of 1, which is equals to 0. And for u of e, or the Euler number, that is ln e, which is equals to 1. So our integral would be, so rewrite this one, so ln x dx. So from the situation that we've solved here, so that is just an equivalent of u du, limits from 0 to 1. And so executing this will be just using the power rule, which is equals to u squared all over 2, limits from 0 to 1, and evaluating this would be equals to u, yeah, substituting the value of our upper and lower limits, so that is 1 squared over 2 minus 0 squared over 2, which is equals to, yeah, this is 0, of course, this is just 1/2. So that is our answer. So let me just check if that's correct. So yeah, that is our answer. So okay, for the next one, okay, tangent x dx. So how can we solve this? So we know that in trigonometric identities, the tan x is equals to sine x all over cosine x, right? So if we break down here, this is equivalent to sine x over cosine x dx. So I think in this particular expression, we can use the substitution rule such that the differentiation of the cosine x will be equivalent to negative sine x, right? So by substitution rule again, let's assume that our u here would be cosine x, while our du here is equals to negative sine x dx. And so we need to have a negative value for your du. So what happens here now, if we try to break down to separate the terms so that we can easily substitute, so we need to multiply a negative symbol. So that is negative sine x dx all over cosine x. And here we can easily substitute, that is equivalent to the negative of integral of du over u, which is equivalent to negative of ln u plus c. And we need to take back also for the value of our u here, which is equivalent of negative ln, which is cosine x plus c. Now this is an answer already, but notice here we have a negative sign for our ln cosine x, and by identity this is equivalent also to ln of cosine x raised to the power of negative 1, which is an equivalent also to ln of 1 over cosine x. So in this term, you can also replace this to the inverse of the cosine x, which is what we know is that secant of x is equals to 1 over cosine of x. So from the trigonometric identity. So this is equivalent to ln of the absolute value of secant x plus c. So this could also be your answer. So yeah, you can use this expression also as a new integration formula as I proceed the presentation, so that differentiation of the tan x dx is just equals to the natural logarithm of the secant x plus c. Another integration formulas would be this expression, no? The integral of b raised to the power of x dx is just equals to b raised to the power of x all over natural logarithm of b plus c, wherein you have a condition that your b as a constant should not be equal to 1. So why is that? It's because in this part, if you substitute the value of your b here as 1, it will become to 0. And what happens if you divide a 0 or you have a denominator of 0, it will just become indefinite value, or it becomes infinity, and we don't have an equivalent value for that. So it means that we cannot solve it. So yeah, our condition should be like this. So b is an arbitrary, so it can be any value. So yeah, so yeah, example for that would be evaluating this. So the integral of 2 raised to the power of x dx would be equals a for limits from 0 to 5. So solving the indefinite integral, so as I roll back, so the equivalent is just bx ln, or all over ln b. So this is just equals to 2 raised to the power of x all over ln 2, limits from 0 to 5. Okay, so what happens here, we substitute the value of your x. We just take out the constant, so that will be 2 raised to the power of 5 minus 2 raised to the power of 0, and that is 1 over ln 2. 2 raised to the power of 5, I think that is 32. Yeah, that is 32 minus 1, that is equivalent to 31 over ln 2, and that is our answer. Okay, so let's proceed. So integral of 1 over the square root of 1 minus x, where dx is just equivalent to the arc sine of x plus c, and for integral of 1 all over x squared plus 1 dx is just the arc tangent of x plus c. So this is just the reverse of the formulas from your differentiation formulas, so don't be don't be hesitate with this. So this is just taking the inverse of the formulas that we get from the previous semester. So okay, let's well, this is just the one of some of the formulas that I've taken, but also there is an equivalent formula for the cosine, the cosecant, the secant, and the cotangent. So yeah, be remind for that formulas. So example. So find an integral of 1 all over the square root of 1 minus 4x squared dx. Limits from 0 to 1 4. So yeah, think we should probably use the differentiation formulas, integration formula derived from the uh, sine, arc sine. So we know that uh, 1 over the square root of 1 minus x squared dx is equals to the arc sine of x plus c. And so if we try to look at the integration given problem, um, to 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 realize that this is a value of an inside a, your x value here has a value of negative 4x, right? So if we try to uh, manipulate the equation, that is equivalent to the square root of 1 minus 2x raised to the power of 2, no? A quantity squared. So this is just equivalent to 4x squared. And so this is this particular value should be replaced with a variable u through a substitution rule. So by substitution rule, we know that your u here is 2x and your du here is 2dx. So here this is an equivalent of 1/2 of the integral of 0 to 1/4 1 all over square root of 1 minus u squared, then 2dx, right? So 2dx here becomes u, so this becomes du. So, and also your upper and lower limits should also be changed. So yeah, we need to replace this. Your upper limits at 1/4 is 2 times 1/4, which is equals to 0.5, and your u at 0, which is 2 times 0, which is just equivalent to 0 again. So this is 0 to 1/2 or 0.5. So executing this would be equal to arc sine of u limits from 0 to 1/2. So just directly solve this value. So that is arc sine of negative 1/2. No. Insanity. This is just arc sine negative 1. So minus arc sine of 0, which is equals to arc sine of 0.5 minus arc sine of 0. That is around 1/2 times 165, which is equals to 1 over 12 pi. So that is our answer. Okay, let's proceed. So, yeah, we have here another example. So evaluate the integral of 1 all over x squared plus a squared dx. Since our value is respect with an x variable, so we mean that our a here is a constant, right? Okay. So I think we should use the integration formula for our tangent, which is 1 all over x squared plus 1 dx would be equal to arctangent of x plus c. So yeah, so what will happen now here? So this should be equivalent to 1. So a squared should be equivalent to 1. So so that we could say that this is an equivalent of a tangent here, no? However, what should we do so that it will be equal to this particular term? Okay, so yeah, so what we do now is we need to have an equivalent of 1 and a squared here. So we extract down the a squared, our coefficient, our constant. So your the integral of 1 over x squared plus a squared dx would be equal to the integral of 1 all over a squared quantity. Since we are taking out the a squared, so the top into x will be all over a squared plus 1 dx. And so our dilemma again here is kani. We need to have like this. So I think this particular situation can be easily solved through substitution rule. So we know that it is just equal to the integral of 1 all over a squared times the quantity of x over a squared plus 1 dx. And by this form, yeah, our u here by substitution rule would be x all over a, and your du should be 1 over a dx. Diba? So 1 over a dx, so we need to have a 1 over a, then we multiply it. Since we are multiplying 1 over a, the reciprocal would be a. So taking out the here in our integral at ipagawas, that is 1 over a squared. So 1 over a squared multiplied by the quantity of a, integral of this should be 1 over u squared plus 1, and since we are replacing here with our 1 over a dx, so this is equals to du already. Ba? So in other words, this is equal to 1 over a squared a times 1 all over integral of 1 over x over a squared plus 1. This is 1 over a dx quantity. Ano? Close bracket. So, muna ang nahitabo dere. So, solving this particular expression here, this is just equal to a all over a squared, that is 1 over a, and this is equivalent to tangent of arctangent of u plus c, diba? So that is our answer. And so if we try to substitute the value here with x over a, this will be equal to 1 over a arctangent of x over a plus c. So that is our answer. So you can make it as an equivalent formula for any kind of value of a as a constant. So, yeah, so you can use this integration formula for that. So why not give an example? So example, yeah. So from the integration formula of this, you can just directly say that this is just equivalent to a here is 3. We know that this is 3 squared, and our x for here should be x squared, diba? So that is equivalent to here, that is equivalent to x4 plus no, let's just correctly write here. This is x squared plus 3 squared dx, diba? And so we write this say by substitution rule. Our u here should be equivalent to x squared, so your dx is equals to 2x dx, and also your a here should be equal to 3, right? So manipulating this term so that we can easily integrate this, so this should be 1/2 of integration of 2x dx all over 2a x squared. Quantity of x squared raised to the power of 2 plus 3 squared. Diba? So we multiply it by 2, so in the outside of the integral we multiply the reciprocal of 1/2. So uh, alongside with the integration formula, this is just equal to 1 all over a, which is 3, arc tangent of your u here, which is x squared plus c. That is your final answer. Let's just confirm this. No. Your x over a pala. So, if you this is sa'yo. So the correct value should be x over a, which is our x is x squared, diba? And yeah, our x squared all over the a, which is the 3. So that is equivalent to 1/3 of arctangent of x squared all over 3 plus c. And that is our answer. Okay, so let's proceed. So recall to you the definition of hyperbolic functions. So this might be useful for translation of integration. So the sine, hyperbolic sine, hyperbolic cosine, so on and so forth. So in the future problems, you can easily substitute the value of your hyperbolic sine, and yeah, it will be just equivalent to exponential of x minus the exponential of negative x all over 2. This particular expression can be easily integrated, diba? You have an equivalent integration formula for this, and thus you can easily convert those expression in these terms. Okay, another example. So the integration of dx all over the square root of 1 plus x squared, limits from 0 to 1. So what we know from the integration formulas is that we have 1 all over the square root of 1 minus x squared, which is equivalent for arc sine. However, we don't have also the equivalent value for the positive one. So what should be particular formula that we could possibly use? So looking back for the differentiation formulas, so the d of the dx of sine, hyperbolic sine of x is just equivalent to the square root of 1 plus x squared square root, diba? So yeah, so this is just equal to 1 all over, no. This is just equals to arc sine man dapat. So arc sine. So arc sine, arc hyperbolic sine of x, diba? So this is just equivalent to arc hyperbolic sine of x from 0 to 1, and so this is just equivalent to sine h, or arc hyperbolic sine of 1 minus arc hyperbolic sine of 0. So, yun naman eh. 4. 1 minus arc hyperbolic sine of 0. That is equivalent to 0.8813. That is our answer. Or just this is arc hyperbolic sine of 1, which is also equivalent to uh, integration, I know, hyperbolic sine identity, which is equal to the logarithmic of 1 plus the square root of 2. That is our answer here. Okay. So yeah, you could possibly scan the integration formula. So I think that the formulas that I give to you is more than complete. So this is how you apply in terms of the inverse functions. So I will be giving also another classwork for this topic, and I will announce possible activity soon. So thank you for listening and see you on the next video.